Chapter 5 in Brown and LeMay deals with thermodynamics, which is something that you'll study again in 1412 if you take 1412. It's kind of an unusual topic. So what happens with thermodynamics is that typically students don't really understand it completely unless they've taken more than one class. And when I say that, I don't mean like taking one chapter in 1311 and another one in 1412. I mean actually a whole semester class and sometimes it may take more than one. So if you don't understand how the things that we're going to talk about in this chapter tie together, I wouldn't worry too much about it. Just try to remember the different parts and try to be able to do the problems in the different parts. And then it may not ever come together for you unless you actually stay in chemistry. So let's go to the next slide and go ahead and get our credits. So the materials here in the lecture notes are going to be primarily from Zumdahl's chemistry and also from Brown and LeMay's chemistry. And the commentary, as the next slide will show, is going to be provided by myself. Next slide. All right, so what we'll talk about, among other things, are going to be things like enthalpy, the first law, state functions, path functions, Hess's law, and that sort of thing. So we'll talk about these in turn. Next slide. And then this slide just gives you these three E's, energy, entropy, and equilibrium, where the one here that's marked entropy is something that you talk about in 1412. Not in this class, so you won't have to worry about this one right now. Some schools and some textbooks do cover entropy in the first semester, but we don't. Next slide. Energy is the capacity to supply heat or do work. So we'll want to remember these here because these are going to turn out to be important. So we're going to wind up seeing a bunch of different relationships in this class and in 1412, and we're going to see that work and energy are two forms of the same thing. When we talk about nuclear chemistry and nuclear physics, we'll talk about how that mass or matter and energy are two different forms of the same thing too. So it's kind of like everything kind of like ties together. So the units that we use for energy and also for work are the same. They're joules. Energy has a whole bunch of different forms. Right now, what we want to talk about is just the two main ones. That'd be kinetic energy, which is the energy that a body has when it's in motion, and potential energy, which is energy that's basically stored and it's available, like your car battery has electrical potential energy that's available to you. So if you go out in your car and get in and turn the key, you complete the circuit and the energy that's stored in your battery can then flow. So that's called potential energy. Next slide. And then you also have these units that we used, or people in different scenarios, people still use these. So calories and also kilocalories, but we're not going to use this at all. So, I mean, this is just for your information. Next slide. Potential energy is energy that exists because of the way something is configured. Like, for example, water behind a dam. If you wanted to let some of the water out, you could, and you could use it to turn a turbine. And if you did that, you could use it to generate electricity. Kinetic energy is like if I pick up a baseball and throw it, then the baseball would have a certain amount of energy due to its motion. It can also have to do in molecules with things like translational motion or rotational or vibrational motion, which are things that we won't talk about here. You do talk about these in great detail if you take physical chemistry. So they depend on the mass. In other words, how much does the object weigh and how fast is it going? And the formula for kinetic energy is 1/2 mv squared. Next slide. Here they're just showing you that if you have you have a ball in position A, it has a certain amount of potential energy, because if you let go of the ball or release the thing that's the catch that's holding it, then it will fall. So once it starts to fall, then the potential energy that it had when it was up here is translated into kinetic energy. Next slide. And then they're just showing a further little bit of example here of what happens. The ball comes down and hits B, and then B now receives the momentum from A and it goes up the hill. So now B has potential energy because it can roll back down. Next slide. And so there are other forms of energy that can be stored, like for example chemical bonds store energy and so forth. Water behind a dam, as we said before. Next slide. So the law of conservation of energy was an old law. They used to have the law of conservation of mass, and then they had the law of the conservation of energy, and they said that mass is conserved and energy is conserved. Now, since we know that mass can go to energy and energy can go to mass, and we'll talk about this when we get to the chapter on nuclear chemistry. We'll talk about it also. That's in 1412, but we'll also talk about it a little bit in this class in 1311. Not as much, but we will mention it. But I'll just say in passing that you can have matter turned into energy, and the formula is E equals mc squared. An example of that would be the hydrogen bomb, or the atomic bomb, where part of the mass is converted to energy of the components of the bomb, the uranium or whatever. When for an old-fashioned atomic bomb, you just blew up a uranium atom and then it would start a chain reaction. And just very briefly, you can also go in the other direction. So if you have some very high energy rays like gamma rays, and it usually would be a gamma ray, then the gamma ray can actually turn into matter, and they do. So you can watch these in what are called cloud chambers, and so you can have a gamma ray and you can actually watch it going across. I mean, not in real time because they're going so fast, but you can see the path that they leave in a cloud chamber, and then you can just watch as they turn spontaneously. They are so energetic that they can actually turn into a pair where one of the pairs is an electron and one is a positron. And so what that's telling us is that there's a very subtle difference between mass and energy, and it's not particularly difficult to go back and forth from mass to energy. So you can think of mass and energy as being two different forms of the same thing. And so we talked about that earlier. So when you say that energy is conserved, it's actually not correct. It's actually mass dash energy is conserved. And that is a true statement, at least as far as we know. So if you take all the mass and energy of the universe and combine them, then that will be conserved. I said a lot about that, and I didn't probably need to say all that. So anyway, let's go to the next slide. Here's another picture of potential energy. So here, over here on the left-hand side, you've got a reservoir. Somebody built a dam across a little creek and made a reservoir. And now you've got all this water which can be released. I mean, this way that they have it here is because it's overflowing, but typically if you wanted to make power out of it, you would have it flowing in a controlled way through a place where you can turn a turbine. But the point of this slide is just to show you that once the water starts to overflow the dam, then the potential energy that you had up here is now converted to kinetic energy here as the water's flowing over the dam. And then once the water hits down here at the bottom, then that kinetic energy is turned into things like noise or sound energy, and also friction as the water hits the rocks. Next slide. So thermal energy is the kinetic energy of molecular motion, heat energy, thermal energy, and that's part of where we get the name of this chapter, thermodynamics. Thermos is a Greek word that means heat, and dunamis is a Greek word that means power, so it's heat power. And a lot of this chapter that we're studying right now, a lot of the theory behind it was developed during the Industrial Revolution, especially in England, where they were using steam power to power, and we'll talk more about this later, but steam power, which was not very efficient, but still it got the job done, but it's just that most of the energy was just wasted. But they would take coal and burn it, and use that heat to boil water and then use the steam to drive turbines. And then they used that in things like locomotives. This was before diesel engines were invented. And then they would use the locomotives to transport things, and they would also use the steam to drive machinery so that things could be made by machine rather than by hand. So that's where a lot of this stuff got started that we're talking about right now. So heat is the amount of thermal energy that is transferred. You can also call it enthalpy. It's transferred due to a temperature difference. We're going to come back to what we said just a moment ago also about the energy. The energy, we said a moment ago that it can be used to do work, which we're going to abbreviate as W, or that it can provide heat. And for some reason, they abbreviate heat as a Q. So, and I don't know why that is. I never have understood that, but that's what they do. So basically, the energy that we're going to talk about in this chapter is going to be made up of work and heat, at least for the purposes of this chapter. So if you added the work to the heat, you would get the energy change for the system, we're going to call it. Next slide. So heat involves the transfer of energy between two objects that are due to a temperature difference. And so it turns out that if you want to know how much energy some body has, then you can take its temperature. Work involves a force acting over distance. Now, what we're going to do here is this is the physics definition, but we're going to change it to something that fits thermodynamics better, because usually we don't deal, I mean, you can, but in thermodynamics, you're usually dealing with pistons. And, like, for example, the steam engines had pistons. So you've got like a piston. So it's easier to use pressure and volume in this chapter when you're talking about how much work's being done than it is to talk about forces and distances. So we'll see how that we can change it over to make it a different formula. So force times distance is a good formula, but we're not going to use it in this chapter. We're going to use another one, and we'll get to that in a minute. Next slide. All right, so we're going to define the system as whatever we're interested in, and you can define the system to be what you want it to be. So if you've got a glass of water sitting on a shelf, you could consider the glass with the water in it to be your system, or just the water could be your system. Once you define what your system is, then everything else automatically becomes what we call the surroundings. So for this chapter, we're going to call the system the thing that we're looking at and studying, and we're going to call the surroundings everything else in the universe. And so if you add the system plus the surroundings, you get the universe. So those are the three things we're going to come back to again and again. Next slide. So here we have a system. You can consider this box with the flask and the green stuff in the flask to be your system, or you can consider just the flask and the green stuff to be your system, or you can just consider the green stuff to be your system. And here they're just saying that it's this green stuff. They're just saying that's our system there. And even the flask and the box and everything else in the whole universe is going to be the surroundings. And then if you add the system to the surroundings, you get the universe. Whenever something goes out, and so what we're going to do is we're going to say, okay, energy for our purposes here is going to be made up of two things. Actually, it would be the change in energy. So when I write this little thing that looks like a triangle here, this thing right here is called delta, or the Greek letter delta. It's the capital Greek letter delta, and it stands for change. So whenever you have a system, the system will have a certain amount of energy. And that'll be a combination of all the different kinds of energy that are in it, like heat energy, and anything else, vibrational, translational, rotational. And so it will have a certain amount of energy, but you can change it by, for example, if you heat it up. Or another way that's not as easy to see that you can change the energy of something is to do work on it. It's a little harder to see that. So what we're going to say for our purposes here, and for thermodynamics in general, is that the change in the energy of the system is going to be how much heat either goes in to the system or comes out, or the amount of work that goes in or comes out. So if you add those two things together that I'm marking, you're going to get the change in energy. It's how much heat did you put in, or how much heat did it lose? And the same thing for the work. So we have to have some kind of a system to determine what are we going to call the heat that, for example, that goes into the system. Like if we heat it up, what are we going to call that? Is that going to be plus heat or minus heat? And so you have to have a convention, we call it, where you just make that decision. You just say, well, every time we do these kinds of problems, we're going to say that if the heat goes in, it's either going to be plus or minus. And different textbooks use different conventions. So in our particular textbook, and I think a lot of the ones that I've used, the convention is as follows. Anything that goes into the system, like for example here, look, we've got this system. It's just this green Kool-Aid looking stuff. So anything that goes into that, we're going to just say it's positive. Okay. So let me say it again. Anything that goes in, whether it's heat or work, is going to be plus. So if you heat it up, that's plus. If you put work into it by, like for example, if you press a cylinder, a piston in a cylinder, if you press it down into the system so that you're doing work on the system, then that's considered to be positive. And then vice versa is also true. If you have a system that's doing work on the surroundings by expanding and then it's pushing a piston up, then that's negative. So anything that's going out of the system, if you have heat going out of the system, then that's negative. So you can write what's called the first law, which we've already stated, and I didn't mention it at the time we stated it, but when we talked about energy being conserved, that's actually called the first law of thermodynamics. Energy is conserved. Now we said it isn't really true, but so it should be mass energy is conserved, but people still say it, and you can't really measure in most chemical reactions the amount of energy that's changed. So I mean, just for the purposes again of this chapter, it's usually just stated the first law is that energy is conserved. So it turns out there's a couple of other ways you can see the first law. In any of them, I'm going to tell you two other ones right now. Any of those are good answers for an exam if you're given like a fill in the blank question where they ask you to write the first law. So you could write, if they ask that, energy is conserved, and that would be acceptable. It would be correct. Or you could write this thing up here that's underlined where I'm underlining right now. Delta E equals Q plus W. That's another way you can write the first law. And then you can also write it the way that it's written where I'm circling right now. Delta E equals the final energy minus the initial energy. All of those are the first law. So I'll just write a 1 here. So that's the first law. That's another way of writing it. Any of those are acceptable. And then there's a couple of other definitions here. I've defined isolated and closed systems. I'll let you look at that on your own. And let's go to the next slide. And so this slide and then the next couple of slides, I think, let's go to the next one. And the next. So those slides were just saying what I had already said. So let's go ahead and move forward for the sake of time. So, and we've already talked about this too. So I'll let you look at this if you want. So if you want to read this, just pause it, but I'm going to go on. Thermodynamic quantities, like just about everything else, have a number and also they have units. And in thermodynamics, we also have either plus or minus. So as we said before, you have to put plus or minus to show whether the heat or whatever is going into the system. So again, if the heat goes into the system, we say that it's plus. So heat in is plus, work in is plus, anything in is plus, and anything in the opposite direction, anything going out is minus. So that's what they mean when they say a sign here. Next slide. So for endothermic reactions, it means you've got to put heat into the reaction to get it to go. Now, we'll talk much more about this in 1412 on the chapter on thermodynamics there. But basically, there are two things, and I'm kind of getting you ahead. So I'm going to tell you something you don't really need to know right now, but it's just useful. There are basically two things that drive reactions, and that's enthalpy and entropy. And you're probably already familiar with enthalpy. If you took chemistry in high school, you talked about the heat of the reaction and you called it H. And it turns out that it isn't really H. That H doesn't stand for heat. The H is a state function, which we'll talk about that later, that somebody came up with. And it's supposed to determine a state function for the heat that we've been talking about, where you can actually look at that and use that as a determinative way to tell whether something will happen spontaneously. But it's not the only thing that determines spontaneity. There's also something called entropy. And because we don't talk about entropy in 1311 here, I don't want to get into it too much, but entropy is, I mean, just, you don't have to remember this right now, but just think of entropy as randomness. And so the more random something is, the more likely it is to be spontaneous. But that's only one of the two things that determine spontaneity. So when I say spontaneity, what I mean is if you leave it alone, it'll happen. I mean, you don't have to do anything else to it. So it turns out that the other thing that determines spontaneity besides the entropy or the randomness is the enthalpy, or the H, which you called heat of reaction in high school if you took chemistry there. So you may remember, if you did take chemistry, that when you have a negative delta H, in other words, a negative heat of reaction, which we're not going to call it that, we're going to call it a negative enthalpy of reaction, that was by convention considered to be exothermic. And when something's exothermic, it means that it'll happen by itself, basically. I mean, almost always. There may be a few exceptions, and there undoubtedly are. And if there are exceptions, it's because that the entropy part of it is just so unfavorable that it doesn't happen even though the delta H would be negative. But for most purposes, you can say that when something has a negative delta H, unless the entropy prevents it, it will be spontaneous. So when you have a positive delta H, it's called endothermic, and that means it won't happen spontaneously. You have to make it happen if you want it to happen. And the way that you usually do that is by adding heat. In other words, you have to heat it up. So there are some things that won't happen on their own, but if you heat them up, they will. And I mean, I can think of any number of examples, but I think you can too. So let's just go ahead and move forward. So when you have an exothermic reaction, it will happen, for most purposes, it will happen spontaneously. Again, you have to take entropy into account. You have to actually add, in some sense, the entropy term to the enthalpy term, and then you get what's called the Gibbs free energy. And that's all stuff we'll talk about in 1412. And that's actually what does determine spontaneity, is the Gibbs free energy. I'm just telling you that so you'll know now, so that you won't be wondering what the heck I'm talking about. But usually if something is exothermic, then it will happen spontaneously, with a few exceptions. So when something's exothermic, we say that they have a negative delta H, which means the enthalpy, enthalpy, is negative, which is just a conventional sign that it's exothermic. So you want to remember that. So this H, what you called heat in high school, we're going to call enthalpy now, because that's the correct name for it. And then whenever your delta H is negative, it's spontaneous, or it's exothermic. Okay, I should say it's exothermic, not spontaneous, because as we just mentioned, but it's exothermic. So if the delta H here, instead of being negative, was positive, then it would be endothermic. So it doesn't mean that it can't happen. It just means that you would maybe have to heat it up or something to get it to happen. Or there are other ways you can get reactions to happen. And then some reactions are just not going to happen, period. Next slide. So is freezing of water endothermic or exothermic? And if you've ever lived up north where it's cold a lot, you may remember sometimes you've been outside and it was really cold, and then it would start snowing and it seemed like it warmed up a little bit, because what's happening is when it snows, the water in the atmosphere freezes, and when it does that, it actually puts off heat. So what's happening is when water, which is a higher heat content, changes, so that's water, and if it changes to ice, ice has less heat than water. And so the heat that is given off here is given off in the form of heat. In other words, it's exothermic. There's heat given off. So anytime you go from a vapor to a liquid or a liquid to a solid, you're giving off heat. You're going down the scale. You're going down the ladder. So like if you go from steam to water, heat will be given off. So whenever steam or water vapor condenses, then heat is given off. Whenever water freezes, then heat is given off. If you go in the other direction, if you go from ice to water, you have to put heat into the ice to make it melt, so that's endothermic. So when ice melts, that is endothermic, but when water freezes, that is exothermic. So just think of it like if you're going down from either from steam to water or from water to ice, then that's going to be exothermic. Next slide. So we've already answered this. Let's go ahead and go to the next slide. Next slide. So here we have an example of a reaction where energy is given off in the form of heat over here. So this reaction happens, and when it does, it happens spontaneously, which means that you can just mix the reactants and they'll react. You don't have to add any heat to it. In fact, it actually gives off heat. So that's what this means. It's giving off heat, so it's exothermic. So when we write the 802 kilojoules of energy, we put this negative sign in front of it. Next slide. So now we need to talk about state functions and path functions. Let's go to the next slide. So the example here is, for example, you're leaving California. So the idea here in this slide is that you're leaving California and you're going to Boston, Massachusetts. And so if you get to Boston and you call your friend in, let's say, California, and he says, "Where are you?" You would say, "I'm in Boston." And it wouldn't make any difference how you got to Boston. So that would be analogous to what we call a state function, and it's just a coincidence that we're talking about states of the union versus these kinds of states. That's just a coincidence. It has nothing to do with that. But so you would be in the state of Massachusetts, but you'd be in Boston. And it wouldn't matter how you got there. So we call something like that a state function, and there's a whole bunch of those. So there's the energy, the internal energy of a system would be a state function. For example, if my temperature was 98.6 degrees Fahrenheit, then that means that that's how much energy I have, and it doesn't make any difference how it got there. It's 98.6 degrees, that's how much it is. So that's a state function. Then if you added some more heat to me, like if you heated me up and I went up from 98.6 to 99 degrees, then I would now be at 99 degrees, and the 99 degrees would be just what my temperature is. Okay, but the difference between the 98.6 and the 99 would be the change in the energy or the change in the temperature. So when we have something like that, it's called a path function. And so back to our example here, if you drove from California to Boston, you could have gone through, looks like North Dakota and Montana maybe, or, I mean, you couldn't have driven the way they have it there, or you could have come down to New Orleans and then gone up to Boston. So in that case, it would be like if they asked you how much did you spend on gas. Well, in that case, it wouldn't matter, because if you went this way, straight across, then you'd spend less on gas, considering that, if you assume that gas prices are the same everywhere in the country, you'd spend less on gas than if you went this way. So that something like that is called a path function. A path function means it does matter which way you went. And there are a couple of those, which I'll just mention. The heat that we've been talking about, the Q, and the work, the W, are path functions. So they're just scalars, they're just numbers. And also we're going to talk about delta H. Now H, and this is one of the things that was hard for me to understand the first time I took thermodynamics. Delta H and H are not the same. The H is a state function, and it's independent of how you got to the amount of enthalpy that a body possesses. But the delta H is a path function. So that little delta in front of that H makes a huge difference, because the delta H is just a number. It's just the change in enthalpy. It's not the enthalpy. So the enthalpy of a body is a state function, and it's that number, that's what it is. But the delta H is just the change that it underwent. So for example, if my enthalpy is 100 kilojoules, and then somehow it gets changed to 101 kilojoules, then my new enthalpy, H, would be 101 kilojoules. But that last change in my enthalpy was 1 kilojoule. That's just a number. So we're saying here that the Q, or the heat, and the W, or the work, are just numbers, and the delta H, which we're going to see later that under most circumstances the Q and the delta H are the same. So we'll get to that, so hold on to that. Next slide. All right, now here we have an example where we're taking two different gases, hydrogen gas and oxygen gas, and we're mixing them together, and they spontaneously react. So what that means is that if they're going to do that, it means that water has to be something that they would rather exist as rather than H2 and O2 gas. So you'll want to remember this. So what that means is that water is more stable than these separated O2 and H2 gases. And let me say it one more time. H2 gas and O2 gas are less stable or higher in energy than water. So like if you were looking at energy on the y-axis over here, and you could just as easily put H here for enthalpy. There's only the only difference between E and H is just the work. So if we just assume that we're not doing any work here, then if we started off with the H2 and O2 gases, they might be up here in terms of their energy, and water might be down here. So there's two different ways we can phrase this, and this is so important. We can say that the water over here is lower in energy than the H2 gas and the O2 gases. Or we can equivalently say that the water is more stable. Okay, so which is lower in energy? It's going to have to be the water. So the answer is the water over here. Next slide. Let's go ahead and go to the next slide. Next. So the more stable form will always be the one that has the lowest energy. So you can think of a roulette wheel. When you drop the ball into a roulette wheel, it will spin around kind of up on top for a while, but eventually it'll fall down to the lowest accessible state it can reach, which is going to be, down in one of the numbers. Next slide. All right, so I'll let you guys go through these on your own. Let's just do this first one. We're supposed to decide if this is exothermic or endothermic with respect to the thing that's underlined. So for the first one here, your hand gets cold when you touch ice. So from the point of view of your hand is losing heat. So from the point of view of your hand, this is actually exothermic because heat's going out of it. Okay, so that's what we're supposed to do for all of these. So I'll let you guys go ahead and do the rest of them as an exercise. Let's go to the 2 slides following. The study of energy and its interconversions is called thermodynamics. Again, we said that this came from the Greek thermos and dunamis, which is heat power. And again, we said this goes back to the Industrial Revolution. The law of conservation of energy, as we said before, is called the first law. It's one of the ways we can do the first law. Next slide. And then I've mentioned this, or I've kind of alluded to this before, but here we're actually going to see this formally. The change in energy, which is just a number, is going to be equal to the heat that either goes into the system or comes out of the system plus the work. And you'll want to remember this. And I mean, for some exams, this may not be on your formula sheet, so you'll have to remember this. And you should anyway, because it's not that difficult and it's really important. So the change of an energy of a system is going to be how much heat goes in and out plus how much work goes in or out, or both. So this, as we said before, this is another way we can write the first law. And also, notice here, let me just mention this before we go on. In this chapter, because Brown and LeMay uses E for internal energy, we're going to use E also, but some textbooks say that internal energy should be abbreviated as U. So just be aware of that. All right, next slide. So thermodynamic quantities, as most things, there's a number and there's also a unit. We've already talked about this before. So like you might have 1,000 joules, but then in thermodynamics, you also have a second thing, or really a third thing that you put in there, and that's this sign in front of it. So it's either going to be negative or positive. Next slide. All right, now we need to talk about work again. As I mentioned previously, we're going to have to come up with another definition for work for this chapter, and also when we get, well, in 1311 we don't do it, but in 1412, if you take it, we'll do a chapter on electrochemistry. And we also have to do another definition for work, not the force times distance one when we get to electrochemistry. So if you take a whole year of general chemistry, you're going to end up with at least 3 different formulas for work. So what we want to do is we want to just derive this, and for the sake of time, and because this is going to have to be converted to a video and then put on YouTube, I probably won't spend that much time on this, but I will leave the slide here and let you, if you want, pause it. But basically what we want to do is we want to get a definition for work that matches this kind of a system that I'm circling. So force times distance could work, but it's just tedious. So let's change it to something that is more useful for thermodynamic purposes. And so what kinds of things would we be able to measure readily? Well, in thermodynamics, we can measure volumes and we can measure pressures. And so if we have a pressure of 10 atmospheres, for example, we can measure that. Same thing for the volumes. You know, for example, here for the cylinder, you're already going to know what the diameter is, and then all you have to do is measure how far up or down the piston moves. So if we could get a formula for work that involved pressure and volume, it would be much better. And it turns out that we can. And so without spending a lot of time on this, we basically start with a basic definition in physics of work, which is force times distance. And then we also start with a basic definition of pressure, which is force per unit area. And we rearrange this definition to get force on one side by itself, and we wind up with force equals the pressure divided by the area, which we then substitute into this definition. So now we've got work as the force per area times distance, which winds up being, the pressure per, let's see, how was that now? The pressure is the force per unit area, so the force is the pressure times the area. So we substitute in the pressure times the area for force. So that F right there becomes the pressure times the area. So now we have the work as the pressure times the area times the distance moved, but we're going to substitute delta H over here for the distance moved by the piston. And so what we wind up with is the area of the base of that volume, that cylindrical volume, times its height, which is the same thing as the volume. And that's exactly what we want. So we wind up here, we've got a delta sign here because the H is changing, and we just kind of bring that down with the rest of this so that we wind up with pressure times the change in volume, and that's going to be our working definition for work in thermodynamics. The only other thing we need to do is we need to put a minus sign here, which we'll see this on the next slide. The reason we have to put the minus sign in again has to do with convention, because if you expand, for example, this way, if you start off with this volume down here, and then if you expand that, then your volume change is positive, right? But according to our convention we mentioned earlier, you would be doing negative work, because we said that whenever you do work on the surroundings, it's negative. So to take that into account, we put a negative sign here. that shows that whatever sign the delta V has, then the work is going to be the opposite. That's just a convention, but you can't forget it or you'll get the problem wrong. Okay, next slide. And this is just showing what we've already mentioned, so let's just go on to the next slide. So here's what we're going to wind up with, and you'll want to remember this. And I don't think this is on your formula sheet. Work equals minus the pressure times the change in the volume. Okay, next slide. So which of the following performs more work? We have a pressure of 2 atmospheres, and it's expanding from 1 liter to 3 liter. Well, so the work here is going to be minus P delta V, which is going to be minus 2 atmospheres times the change in volume, which is plus 3 liters, so it's 6. So it would be minus 6. Whereas for B here, we've got a pressure of 3, so it would be minus the pressure. That would be minus 3 times the change of 2, because you're going from 1 to 3. 3 minus 1 is 2, so that would be minus 6 liter atmospheres. So, I mean, we're not going to use liter atmospheres, but we'll see later how to convert that to another more useful unit. But for right now, we'll just call it liter atmospheres. But the thing is that the answers are the same for both of these. So neither one of these performs more work. They both perform the same amount of work. Next slide. Okay, next slide. Determine the sign of delta E for each of the following. An endothermic process means that delta H is going to be plus, and then it performs work. So that means that the work is going to be negative. And if it's endothermic, that means the heat is going to be positive because it's going into the system, right? So if the work's quantity is greater than the heat's, that means the negative is greater than the positive. So the sign would be negative for this one. On the other hand, if it's the other way around, then the work, which is negative, is less than the heat, then the heat is going to predominate. So the sign is going to be positive. And I'll leave the second one as an exercise. Next slide. Next slide. And this is just showing you a picture of how this could happen. For example, here you have a reaction, and you've got the reactants on the left, the products on the right, and the total number of numbers of molecules on the left is 1 plus 5, which is 6, and on the right is 3 plus 4, which is 7, which means you have more molecules on the right-hand side. So they're showing here that the volume would actually increase here, all other things being constant. So next slide. All right, so expansion work, we've already talked about this. I'm just going to move on to the next slide. Now let's do this one. Consider the combustion of propane, which is natural gas. That's C3H8. C3H8 plus 5O2. Remember, whenever you burn something, we call it combustion. It always reacts with O2 out of the atmosphere. It always produces water vapor and CO2 gas. So when you have this kind of a reaction, they usually don't give you this part. They want you to remember that part, and they want you to remember that you're always going to make CO2 and H2O. You may have to do that on one of the tests. So here they're telling us the delta H value. That's negative. That means heat's given off. Well, we knew that already, right? That's why we burn propane, right, is to get heat. And it's minus 2221 kilojoules per mole. If we assume that all the heat comes from the combustion of propane, calculate the delta H if we only had 5 grams of propane. So to do this problem, we're just going to look here and see that we have 1 mole of propane, and it's producing it's producing 2,221 kilojoules. So that's for 1 mole. But now they want us to figure out how much it would produce if we only had 5 grams of it. So what you're going to do is basically divide 5 grams divided by how much the molar mass would be if you had 1 mole. Here, well, if you had 1 mole of C3H8, it would weigh what? 3 times 12 plus 8, which is going to be 44. So you would just divide 5 by 44 to see how many moles you actually have. And that's about 1/9, or like, what is that, 0.11 or something. So anyway, and then when you get that, so you would go ahead and do that on your calculator. And then when you get that number that it's going to be like something like 0.1 something, then you would just multiply that times the delta H value here, which is minus 2221, and that will give you your answer. Let's go to the next slide. And next. All right, so we've already talked about this. Let's go down to the bottom here and pick up at the stuff that we haven't talked about yet. So delta E is Q plus W, and if we start rearranging this a little bit to get Q on one side by itself, and if you're wondering why we're doing this, it's because it makes it easier for us to work with it. So we put Q on one side by itself by subtracting W from both sides. And then we can substitute in, so what we would get then would be Q equals delta E minus W. And that's right here in the middle. So right there. And then if we substitute in minus P delta V for W, now remember we did that a few slides back, then we get that delta E plus P delta V there instead of what we had before. So we get this, and this is really important. So again, you'll want to memorize this. Q equals delta E plus P delta V, where the P delta V thing is the work rewritten in terms of pressure and volume. Let's go to the next slide. So when we have that, there are two different possible ways we can write this. And you have to kind of use common sense here. So one way that this can happen, I really should be back on the previous slide, but I can't get back to it. So one way this can happen is if you're at what's called constant pressure, which you probably are. So most experiments that you do in the chemistry laboratory, physics lab or whatever are done at constant pressure. And what that means is that somewhere in your apparatus you've got an opening to the atmosphere. And if you have even a pinhole, is enough to allow atmospheric pressure to get into whatever you're using there for your experiment. So the vast majority of experiments are done at constant pressure. However, it is possible, and we'll see some pictures later either in these slides or also in the work problems, it's possible to do it a different way. And we'll talk briefly about that, but it's not something you're going to see very much in terms of test problems. But it's also possible to do this at constant volume. And the way you do that is just make like a container and bolt the lid down so the volume can't change, and then do your experiment in there. And so when you do that, you're actually allowing the pressure inside that box to vary. So it's not constant pressure, it's constant volume. And that's what we're looking at right here where I'm drawing this box. So when we have that situation, we put a subscript V under Q. Remember, Q is the heat. And this is going to be the heat at constant volume. And when you do that, whenever you've got constant volume, over here for your work, remember the work was P delta V, but the delta V means the change in V, the change in volume. But if you're at constant volume, the volume doesn't change, so the change in volume is just 0. So when you multiply that by your P over here, you still get 0 because 0 times anything is 0. So this whole term actually drops out. So in the unusual circumstance that you're at constant volume, and in order to do that, you have to make a special apparatus that has a bolt-down lid, and that's called a bomb calorimeter. So problems that are dealing with this will usually give you a clue by telling you this is a bomb calorimeter or it's constant volume. And those are very rare. Most of the overwhelming majority of the problems deal with constant pressure, which we'll talk about down at the bottom of the slide in a minute. But when you do have these unusual situations, then the QV actually reduces down just to the delta E part. So you can just say that the change in the internal energy, remember the E here in this particular book is called the internal energy. It's abbreviated as E. So the change in the internal energy is just going to be the Q. And so you can see here that, again, this little delta makes a big difference because E by itself, just E is a state function. But the delta E, again, is equal to Q sub V, so that's a path function. And so Q at constant volume is just delta E. So you just figure out what the change in internal energy is, and that will tell you what Q is, or you can figure out what Q is, and that will tell you what delta E is. We can do the same thing below here. Now, the more common scenario by far is that you're going to be at constant pressure. Just about everything you do is at constant pressure. It just means you're doing something and you're exposed to the atmosphere. So here we're going to write the Q with a P subscript, where the P stands for pressure, right? And in that case, none of this stuff here, the delta E doesn't go away or vanish, and neither does the P delta V. So you just leave it like that. So I'm just going to go ahead and go a little bit ahead and just tell you that when you have this situation, it's so common that they gave this Q thing here a special name and called it delta H. So that's where the delta H, as in the change in enthalpy, comes from. And so what they designed this to be was H is going to be a state function that tells us what the heat content or the enthalpy is. So H by itself without that delta is a state function. Sorry about that. Is a state function. So the only thing that matters is what is it right now. So if it's 1,000 kilojoules, it's 1,000 kilojoules. It doesn't matter if it started at 1,001 and dropped, or if it started at 999 and went up. It's a state function. Once you add that delta to it, you put the delta in front of it here, then it's no longer a state function. This was really hard for me to understand, and it didn't help that I had a crap teacher. And he chose a crap textbook. And that's the way it always seems to work, is those rare occasions where you get a really worthless teacher, they always manage to somehow choose a textbook so that it's worthless. So I'm just kind of venting a little bit here. So you can't use the textbook either. So anyway, so when we have this situation here, it's very common. And so you'll want to remember this. If they give you delta H for some reaction here, then if you're supposed to use Q in a formula, you have to remember that the delta H and the Q are synonymous. And that's actually going to be most of the time. Okay, let's go to the next slide. And so I anticipated this and preempted it. So let's go ahead and go to the next slide, because we've actually talked about this already. So, and then this is just going to be the same thing. So let's go ahead. I'll let you pause there and read if you want. Otherwise, let's go to the next slide. So some other state functions here, in addition to the enthalpy. So state functions would be things like enthalpy. Let me just list a few of them here. Internal energy. And then we talked very briefly about the entropy, which that's abbreviated as an S. You don't really need to know these yet. As I mentioned, that's 1412 stuff. And then there's another thing called G, which is the Gibbs free energy. Again, that's 1412. And then other things like the Helmholtz energy, which is abbreviated as an A. And there are some other ones. There's a whole bunch of state functions. And so they don't depend on how you got there. And as far as path functions, work, heat, and then also the delta H, not the H, the delta H or the delta E are also path functions. So the four that we really know of as far as path functions would be Q, W, delta E, and delta H. Next slide. All right, and then so what this slide is saying is basically we can do measurements at a certain temperature and pressure, and that way they'll be standardized so that people around the world know what the value of the delta H for a reaction would be at a certain temperature and pressure. And so the pressure they chose is 1 atmosphere, which for people in Houston, that happens to be the pressure most of the time, because we're right at sea level. I mean, you drive around Houston, I think Deer Park, which is a suburb of Houston if you're not from Houston, they actually have the elevation on their street signs, and it's usually like 5 feet above sea level. So basically, in the Houston area, and most of southeast Texas is on the coastal plain, it's right at sea level, which is one of the things that makes it so miserably hot in the summertime, is because there's no elevation. The pressure, anyway, that's neither here nor there. The pressure is about 1 atmosphere. So that's the pressure they chose. So they do these at 1 atmosphere, and they do them at what they call standard temperature, which for this chapter, standard temperature is going to be 25 degrees centigrade. So when they write the values in these textbooks or in these databases, they write them where they've, if possible, they've done them at 25 degrees or centigrade or 298 Kelvin and at 1 atmosphere pressure. And if any solutions were involved, they did them with 1 molar solutions. And that is called the thermodynamic standard state, and it's abbreviated or symbolized by a degree sign. So instead of writing delta H, or just an ordinary delta H, which wouldn't necessarily be at 25 degrees centigrade, you write it as a delta H with that degree sign on top. And that degree sign right there means you did it at standard conditions. Now we're going to talk about standard temperature and pressure when we get to the ideal gases in chapter 10. And you'll have to be careful because the standard temperature for ideal gases is different from this chapter. So you'll want to watch out that you don't confuse those two. Okay, let's go on to the next slide. So the most stable form of a substance when you're at room temperature, 25 degrees centigrade, is about 77 degrees Fahrenheit, which we're considering to be room temperature. 1 molar concentrations. There should be a space right there. So the thermodynamic standard state is just defined this way, as we said before. Next slide. So here we have a picture of 2 different things happening. It's actually the same reaction, but we're getting a slightly different result. Because what we're doing here on top is we're producing water in the vapor phase, whereas here on this reaction, we're producing water in the liquid phase. So, for example, here, the heat that's put off if we produce the water in the liquid phase is 2,219 joules. We saw this earlier. You remember when we did the problem with the propane gas. So why is this number lower? Well, it's because in order to go from the liquid to the gas, you have to use some of this energy here because you're boiling the water. You're boiling water to make it into gas. So you're losing some of the energy that you produce to do that. So the value here is less. Next slide. Just here down at the bottom before we go. That's the degree sign I was talking about. So when you see this, it means it was done under standard conditions. Whoops, I accidentally went right through there. So delta H with that degree sign, which I call it delta H standard. It's just the standard conditions. You did this at standard conditions, and this is what you got. And the reason for that is so that people can do the same experiment no matter where they are in the world, no matter what their elevation is, and expect to get the same answer. Or if they don't do it at the same conditions, then they can make an adjustment. Next slide. So we can do some definitions here. So you did this in high school if you had chemistry. You called it the heat of fusion when you melted something, the heat of vaporization when you vaporized a liquid like water. And then if you had something that was a solid that goes directly to the gas phase, that's called sublimation. And there are only a few things that do that. One of them is carbon dioxide. If you freeze carbon dioxide and then start letting it be out in the open environment at normal temperatures, then instead of melting and making a little puddle of liquid CO2, it doesn't do that for some reason. It actually turns into a gas directly. So that's like a combination of fusion and vaporization combined in one step. So the heat of sublimation, or we're going to call it enthalpy, is when you go directly from a solid to a gas. These are abbreviated as delta H fusion, where the fusion is written as a subscript, delta H of vaporization, and delta H of sublimation. If they had degree signs, that means that somebody did this at standard conditions. Now, to do standard conditions, you have to be at 25 degrees centigrade, right? So unless your stuff actually happens to melt or vaporize exactly at 25 degrees, you wouldn't do that in these cases. Next slide. So here's another picture of what we were talking about on the previous slide. When you melt something, you're going from a solid to a liquid, or you can freeze it by going in the other direction. When you vaporize, when you vaporize something, you're going from the liquid to the vapor. And then if you go in the opposite direction, that's called condensing it. And then sublimation means you're going directly from the solid to the gas, and that's going to include the heat of, or the enthalpy of fusion and the enthalpy of vaporization. If you go in the opposite direction here, that's called deposition. Next slide. So here we have an example where we're going in one direction, and this is going to be a spontaneous thing because we have a very high delta H and it's negative. So this is exothermic, and it'll basically be spontaneous the way it's written. If we wanted it to go in the opposite direction, we might be able to do that. We might be able to by adding heat, because this is going to be endothermic. So what they want you to notice here is that if you reverse the direction of a reaction as they've done here, the sign changes on your delta H. These were done under standard conditions, so they're both delta H standard with that degree sign there. So what's changing? The sign is changing. If you're going this way with the AL on the left, then it's an exothermic reaction. And so you're going to have a negative delta H. If you turn it around and do it the other way, then it's going to be endothermic, which means you've got to put some heat in over here to get it to happen. So you have to add that. That H there stands for enthalpy or heat. So the deal is, and the reason they're telling us this is because we're going to have some problems that we're going to do later on where we're going to be given like a reaction like that one, and for various reasons we're going to have to reverse it. And so when you do that, you just have to remember, when I do this, when I reverse the direction of the reaction, I have to remember that I've got to change the sign for my delta H. So if it was originally negative, I've got to change it to positive. The number stays the same, but you have to change the sign. If it was originally positive, you change it to negative. Next slide. Now, we said earlier that we can do thermodynamics either at constant temperature, constant pressure. Constant volume or constant pressure. And actually, the Navy and the Air Force have been experimenting with things that are neither of those for what are called rotational combustion or rotational detonation engines. And I was involved in that for a while, that research with a project that was a cooperative project between the school where I teach and some other universities. But that's something that's very exceptional. So most of the time it's either going to be done, any experiments in thermodynamics are basically going to be done either at constant pressure or constant volume. So notice here that we have a situation where we have a top that is not bolted on here, so it's just loose. You've also got a little tiny hole probably where the stir and where the thermometers are. So I mean, that's plenty for the atmospheric pressure to get inside there. So this would be done at constant pressure. So again, as I said before, most of the experiments will be done this way. Next. Whereas on the other hand, if you bolted this thing down, which we don't see any bolts, sometimes they'll actually show bolts here. Like, so there's a bolt there and they go all the way around. And they're not showing that here, but they're telling us that this top is fixed or bolted down or whatever. Then this can't move, so this is going to be done at constant volume. So something like this is called a bomb calorimeter. So when you have a problem like this, they'll usually give you a clue, like they'll say, hey, you know, this is a constant volume thing, or this is a bomb calorimeter. If they tell you it's a bomb, B-O-M-B calorimeter, then what that means is that it's constant volume. So you do the problem slightly differently. Next slide. All right, now let's talk about a couple of other definitions. Heat capacity is the amount of heat that's required to raise the temperature of an entire object, whereas the specific heat is the amount of heat that's required to raise 1 gram of that substance. So usually these come into play as follows. Like if you have a coffee cup with coffee in it, then in order to raise the temperature of the coffee, you have to multiply how much there is in terms of how many grams you have of the coffee times the change in temperature times the specific heat here, which we're talking about right now, which is abbreviated with a lowercase c. So you would have to multiply all three of those things together to get how much heat it would take to raise it, for example, 4 degrees. So if you had 100 grams of coffee and you want to raise the temperature by 4 degrees, you'd have to have about 100 grams times 4 degrees times 4.18 joules per gram degree centigrade. And that's the specific heat. So the specific heat of water is 4.18 joules per gram degree centigrade. So you would multiply by the number of grams, which we said was 100, and then times the number of degrees you want to raise the temperature, which we said was 4. So it would be about 100 times 4 times 4. So that would be about 1,600 joules that you would have to put in to raise it 4 degrees. Okay, the difference between that and the heat capacity up here is that the heat capacity would refer, for example, to the coffee cup, where you're doing the whole thing as one object. So in other words, what I'm saying is if you want to figure out how much heat you'd have to put in to raise the coffee cup's temperature 4 degrees, you would just multiply the 4 degrees times what's called the heat capacity for the coffee cup, and that's delineated in units of joules per a number of degrees you're trying to raise it. So in other words, all you have to do is multiply the heat capacity times the number of degrees. So for example, if the coffee cup had a heat capacity of let's say 500 joules per degree, and you want to raise it 4 degrees, you'd have to multiply 4 times 500, and that would give you 2,000 joules you'd have to put into it. So the heat capacity typically is going to refer to the container, or what we call the calorimeter. So when we say calorimeter, and I actually mentioned it on the previous slide and I forgot to explain what I meant by that, but when we say calorimeter, we're talking basically about the coffee cup if you've got coffee in it. In other words, the thing that's actually holding a solution. So you have basically two different things you have to worry about. You have in a coffee cup with coffee in it, you've got the coffee and the cup. And so to do the problem completely, you have to do both, and they're done differently, as we just mentioned. However, in some cases, they'll tell you to assume in a problem that the calorimeter that you have in that problem is a perfect insulator, which means it won't change its temperature. So you don't have to worry about the heat capacity for those kinds of problems. Let's go to the next slide. So the heat capacity is extensive, and again, it's how much heat you have to put into like a coffee cup or something like, or a glass, like a drinking glass, to raise its whole temperature. And the reason they do it differently from the liquid inside of it is because it just doesn't make sense to do it per gram of the coffee cup. I mean, why not just go ahead and see what the coffee cup weighs and then incorporate that into your calculation from the get-go. So that's what they do. So again, to abbreviate heat capacity, and you'll have to keep these terms straight, heat capacity is the thing that deals with the coffee cup. It's a capital C. The specific heat would be the coffee inside or the tea inside or whatever, and it's a lowercase c. And in some other textbooks, they'll also use S. Next slide. And here are some examples of various specific heats for different things. You can see down here at the bottom I've got a red arrow by water because it's so much higher than everything else. And so we're running out of time, so I'm going to have to say this really quickly. Water doesn't heat up very fast, and it doesn't cool off very fast. So if you're living in Galveston in the summertime, it's going to take a heck of a lot of heat to raise the temperature of the water up. So typically in the daytime, in the summertime, like in Galveston, the land heats up, but the water doesn't heat up that much. So, I mean, it might be 95 degrees on the land and it might only be 77 in the water, because water has a very high heat content or specific heat. In other words, like in order to heat up water, in order to boil it, you have to put a lot of heat into it. It just doesn't change its temperature that much, as opposed to something like copper here. So that's why some people use copper to cook with, is because it has such a low specific heat. In other words, if you just put a little bit of heat into copper, you're going to heat it up a lot because its specific heat is so low. And what that means is it's easy to heat it up. All right, so the fact that water takes a lot of energy to heat up means that in Galveston or places like Galveston, Where you're next to a large body of water, also places like Chicago are the same way, because even though they're not next to the ocean, they're next to very large bodies of fresh water. The water, whether it's fresh or salt, it still doesn't change its temperature very rapidly. So it has a cooling effect in the summertime, and it has a heating effect in the wintertime. Let's move on. So here we have an example of a can of soda, and we're going to assume for the sake of this problem, and for all of our problems really, that the soda has the same specific heat as water, which was 4.18. So here it is right here. So the specific heat of water is 4.18 joules per gram C. We're going to always assume that if we're dealing with coffee or tea or soda, that it's the same. And it basically is. So we want to cool this from 25 to 3. So our change in temperature here is going to be minus 22 degrees. We want the minus sign in there because we're cooling it. So we're going to have to know how many grams we have, which is 350 here given, times the change in temperature, which is minus 22 degrees centigrade, times the specific heat. Now when you multiply your specific heat times your mass in grams, the grams are going to cancel. And then when you multiply by your delta T, the C's here are going to cancel. So the only thing that's going to be left in your answer is the joules. And that's what you want. You want to know answers for heat in terms of joules, because that's a form of energy. It's heat energy. Same thing for work. So work will also wind up with an answer in joules. Okay, next slide. So you multiply your specific heat times the mass in grams times the change in temperature. And it turns out to be minus 32,000 joules, where that negative sign comes from right there, where you kept the negative sign in your 22 degrees. It was negative because the temperature was dropping. And then you can round that if you want to minus 32 kilojoules, where the kilo means 1,000, so it would be 32 kilojoules. Next slide. So this concept check wants us to take water at 100 grams of water at 90 degrees and add it to 100 grams of water at 10 degrees. Now, this one's just common sense. If you add 100 grams of water at 90 degrees to 100 grams of water at 10 degrees, you're going to end up with 200 grams of water at 50 degrees. So the answer here is going to be B. And it doesn't require a lot of thought. It's just a matter of looking at it, and you have the same amount at both ends. You've got this 100 grams at 90, 100 grams at 10. So you have the same amount, and it's water in both cases. So you're going to wind up right in the middle. So if you wanted to calculate it, you would just add 90 plus 10 and divide by 2, and you're going to get 50. However, let's go to the next slide, and the next one. This one is a little different. So now you have a styrofoam cup, and in this one you don't have water on both ends. You've got water at 10 degrees, so that's at the lower temperature, but you've got iron at 90 degrees. So what we can remember from that chart that had the different specific heats is that iron is going to change its temperature more than water. Water won't change very much. So if the water is originally at 10, it isn't going to heat up very much. So it won't make it all the way halfway to 90, which would be 50. It's going to be between 10 and 50 here. And the reason for that is because the iron is going to cool down much more than the water will heat up. Next slide. Next. So now we're supposed to find the final temperature of the water, which I'm going to set that up for you. So what you want to do is you want to call the final temperature here X or TF or whatever you want to call it. So what you want to do is you want to multiply for each of these two things you have in the system. You want to multiply the specific heat of that thing times how much there is in terms of its mass, and then times the change in temperature. But you won't know the change in temperature. So before we talk about the change in temperature, let's just back up for a minute quickly. So for the water, you're going to be multiplying its specific heat, which is 4.18 times 50 grams times its change in temperature. The change in temperature for the water will be whatever the final temperature is minus 10. And then that's going to be equal to the same thing for the iron ball. So for the iron ball, it's going to be 50 grams times its specific heat, which is not 4.18, it's 0.45 here. and then times its change in temperature, which is going to be 90 minus the final temperature. So that's how you set it up. And then all you do is you solve here. You've got one equation with one unknown. So you go ahead and just solve for your unknown, which you can either call it x or you can call it TF or whatever you want to call it. So I'm going to guess it's going to be somewhere around, well, I can't actually remember that. Let's go to the next slide. Next. So it turns out that it's only 18 degrees. Look at that. So that means that it drops the iron ball from 90 degrees all the way down to 18, and the water only heats up 8 degrees. So, and that's what should be expected. I mean, the difference again between metals, which heat up and cool off very quickly, and water. Let's go to the next slide. Running out of time. All right, Hess's law next. All right, so just to sum this up very briefly, Hess's law is a little trick that we can use when a reaction occurs in 2 or more steps. And what I mean by that is, let's say that you've got a reaction where you have to have 2 different steps in the reaction. So you've got the overall reaction, which is the way it would be written in your textbook, and then you've got the actual way it happens, which isn't the way it would be written in your textbook, but it's the way that it actually happens. And there are any number of examples that we could list here that would show that, and we'll see those as we go along. So it might be possible that you could actually measure, for example, let's say the overall reactions change in enthalpy and one of the 2 steps in what we're going to call the mechanism, or the actual way it happens. But you can't measure, for whatever reason, physically it's impossible to measure the delta H, we'll call it, which is the change in the enthalpy for the second step. Then you can use this thing that's called Hess's law, which you'll probably want to try to remember that if you can, just in case the problem tells you to use Hess's law, but you'll probably be able to figure it out anyway. So let's go to the next slide. So here's an example of what I just said. So if you look here at the top, this is the Haber process, and we'll come back to this again and again, all the way through 1412. So it's 3H2, and let me just look at this and see if it's balanced, and it is. So 3H2 plus N2 is 2NH3, where this NH3 is ammonia. So what this is actually producing is ammonia gas. The delta H here is minus 92.2, where somebody was able to measure that, so they just took the H2 and N2 gas and reacted them. But it doesn't actually happen the way it's written here. The way that it actually happens is written here in these 2 steps. And when you add these 2 steps together, you get the thing down here at the bottom, this thing right here, which is equivalent to the way that it actually happens up here. And it just lost that. There we go. So those are equivalent. If you'll look, they're the same. So what we're saying here is that if I add everything on the left of this arrow to everything on the left of this arrow and put it, down here somewhere, and then if I add everything on the right of this arrow and put it down here, then if I cancel everything that's on both sides of the arrow, just like you would in algebra, which in this case would be the N2H4s, you're going to wind up with N2H4 on the left and the right, so you just cancel them. Then you end up here with 2H2 plus H2, which is 3H2 plus N2 on the left, which is what we see here. And on the right, we just end up with the 2NH3. And so again, notice that that matches this, the one written across this row matches the thing at the top. And that's what we want. Somebody was able to figure out what the delta H of reaction, and this is standard conditions here because of the degree sign. They were able to figure out what the delta H of that reaction was. And they were also able to figure out what the delta H of the second step here was in our mechanism. But they couldn't figure out what the delta H was for the first step, but all you have to do is realize that if you add this step's delta H to this step's delta H, you should get the delta H for the combined reaction, which is this one. So in other words, if you start with this one, which is minus 92.2, and subtract away this one, you're going to get the one on the top. And so anyway, it's very simple, but it's called Hess's law. So if you do that, you're going to start off with minus 187, and you're going to actually be subtracting, or let's see, actually it would be minus 92, and then you're subtracting a minus 187, so that looks like it's going to be plus 95. Let's see if I'm right. Next. And here is your answer. So yeah, it's plus 95. Let's go to the next slide. So if a reaction is reversed, as we said before, you can do that, but the sign is changed. If it's negative, you change it to positive and vice versa. And we've said this before. So next slide. Whoops, I was afraid that was going to happen. Okay, so I can't go back. I couldn't get this thing to move. And then, so I clicked it a couple of times to try to get it to move, and it moved twice. So I've got a slide that I skipped. Actually, there may have actually been two of them. So anyway, what you're going to have to do for this problem, I'm just going from memory, is they gave you a couple of things that would be added together to get a certain reaction. So I guess this must have been the reaction we're trying to get. And we're trying to get to this reaction by adding these two reactions, this one to this one. And we were given some initial values here for the delta H for that step and for this step. And so what we're trying to do evidently is we're trying to find what is the delta H going to be for this. All right, so we're going to do this one similarly to what we did just before. We're going to try, though, in this case, to get this reaction on the bottom by adding the two on the top. But if we just add them the way they are, it won't work because the numbers won't come out right. So the way that these are written here, and I don't know if this is how it was initially, so if you have, well, you won't be able to see it on YouTube either because I went through them so quickly, but if you have the lecture notes, you can pull these up. But what we want to do is we want to get these two in the form such that if we add them together, we get the thing down here at the bottom. So there are two different things you can do to make it work like that. One of the things is you can multiply through everything in a reaction by the same number, or you can also reverse the direction of a reaction if that helps. And so if we're just looking here, I can see the O2s are on the correct side, and it looks like the H2s are going to wind up canceling out. And the N2 here is on the correct side already. So I don't know if they've already reversed this or if that's the way it was, but I'm going to guess it was already that way. And then H2O is on the correct side, and then H3 is on the correct side. So I'm just going to take a guess that we didn't have to reverse anything, but if we had, then if we reverse the direction of the reaction, remember we have to reverse the sign. So for example, here it would become positive instead of negative for the 46. In this case, it turns out that if we multiply the top reaction by 4, then that's going to become 2N2 plus 12 halves H2, which is 6H2. And then 4NH3. And we also have to multiply the delta H over here by 4 as well. So we have to multiply that number right there by 4. And the reason is because we multiplied all of these numbers over here by 4. Now if we do that, we're going to wind up with 6 H2s on the left of the top reaction here. But it isn't going to cancel out the H2s here because there's only 2. So the next step is probably going to be that we're going to now multiply this whole reaction by 3. And so let's just go on to the next slide. And if we do that, we'd have to also multiply the delta H for this step by 3 as well. Let's, since I didn't get in on the beginning, let's go to the next slide. And yeah, that's correct. So we have to multiply that one by 3, and then that's going to give us 6 H2s here. So this is going to change to 6. And multiplying this one here by 4 here changes that one to 6. So we're going to have 6 H2s on the left, and we're going to have 6 H2s on the right when we add it together. And so we'll wind up with a situation where we can just cancel that and cancel that. And here we're going to have a 4 for the NH3 and a 3 for the O2, and a 6 for the H2O here, so this becomes 6. Right, so hopefully you can see what we just did. We just multiplied through and got the numbers so that we get what we want down at the bottom here. But don't forget that when you do this, you have to then multiply this number by 4, so that's going to be like about minus 200. And then you have to multiply this by 3, so that's going to be like 1500. So you would then take the new number here and add it to the new number here to get this delta H down here, which is what we're trying to get to. Next slide. So yeah, when you add these two numbers here, you get the right reaction if you add these two reactions after we modified them. And don't forget, if you have to, you can also reverse these. And if you do that, then you have to come back over here and change your sign. Anyway, so let's go to the next slide. Next. So the delta H here will be plus 1268 kilojoules. Next slide. All right, so the next part here is a series of definitions. So let's go to the next slide. So I'm going to go through these kind of quickly, and if you want to pause, you can. We're right at our maximum time here. We're at 1 hour and 25 minutes, and I don't like to go more than an hour and a half. So I'm going to go ahead and let you kind of read these on your own. I'll read them very briefly. The standard enthalpy of formation of something is just how much the enthalpy change would be to form something. And there's your key there, formation, and it's denoted by subscript F. Next slide. And we've already talked about this, so let's go to the next slide here. And here are some examples of these. So for example, for acetylene, the delta H of formation of acetylene, which is C2H2, is 227 kilojoules per mole. Next slide. So when you have a problem like this, you want to start with the delta H of formation of the products and subtract the delta H of formation of the reactants in order to get the delta H for the reaction overall. And we'll have problems like this, and they're very easy. So here's like a way you can write this: the summation of the coefficients times the delta H of the products minus the reactants. So you'll want to remember this is usually the way things happen in chemistry, at least at our level, is it's going to be products minus reactants. In other words, you take the delta H of the products and subtract the delta H of the reactants. There's one exception to that rule when we talk about bond dissociation energies. You do reactants minus products because there, instead of forming bonds, you're breaking bonds, so you go in the reverse direction. And I'll mention that again when we get to it. Next slide. Here's just a picture of this, which I'm going to let you look at this if you want to, but I'm going to go to the next slide. So using the standard enthalpies of formation, calculate the standard enthalpy of reaction for photosynthesis. So the reaction is 6CO2 plus 6H2O, and this happens in plants, obviously, gives C6H12O6, which is glucose plus oxygen that we breathe. All right, so what is the standard enthalpy of reaction? So to get the enthalpy of that reaction, you can take the enthalpy of the formation of the products multiplied by their various coefficients minus the enthalpy of formation of the reactants. And so where would you get the enthalpy of formation of the reactants or the products? You look them up in a chart. So for CO2 gas, that is going to be 383.5 here, where I got this out of a chart. And then for the H2O, it would be minus 285. So again, you would just look these up in a chart. You just want to make sure that you're looking up the correct form. So for H2O liquid, as we have here, you want to make sure you're getting H2O liquid, not H2O gas, and same thing for the CO2. So anyway, you would start off to get the delta H for this reaction, this whole thing here. You do the delta H of formation of the products, which is this, and then O2. But since O2 is a pure element, it doesn't really have a delta H of formation. It's just that's how it exists at room temperature. So the O2 is actually going to be 0, so you don't even have to worry about it. So we can just kind of get rid of that. So what it is going to leave us with is just C6H12O6. So in your chart, look up C6H12O6. It's delta H formation, and that's going to be this number right here, minus 1260 kilojoules per mole. We have 1 mole of it. There's an implied 1 there. So we multiply by this 1 right here times minus 1260 kilojoules per mole. And that's it for the products because the O value here is 0. And then minus 6 times whatever CO2 gas is. So here, notice your minus sign here. So it's products minus reactants, and then we have to multiply by 6 because of this 6 right here. And then this minus 383.5 comes from the chart for CO2 gas. And then it's minus 6 times minus 285.8 for, this is H2O liquid. And notice that because we have a bracket here, that this minus sign over here is actually distributed through the bracket. So this actually is going to be minus 6, which is what we want. And so you don't have to do it the way they have it here. If you want, you can just write minus 6 times minus 383, and then minus 6 times minus 285 anyway. And then just go ahead on your calculator and do the math and do all of these multiplying and then additions and subtractions, and you should end up with 2755. So the formation here reaction has a delta H overall of 2,755.8 kilojoules, and that's to produce 1 mole of glucose. Next slide. Here, this would show you where we got those values. So for example, one of these was carbon dioxide gas, and it was minus 383.5. Glucose here is where we got its value. And I think that we had seen this chart before, right? Yeah, we had. And then H2O, which was in the liquid form, this is where we got that value. So here's where we got the 285, here's where we got the 1260, and here's where we got the 383.5. Now, why isn't O2 on here? Again, because anytime you have a pure element in the form that it would exist in at room temperature, which for oxygen would be as O2 gas, then its formation energy is going to, or its formation enthalpy will be 0. Next. So let's do this one real quickly. We're a couple of minutes over. So here's our reaction. We want to find delta H for this reaction. So delta H for this reaction is what? Well, it's the delta H of formations of the products minus the reactants. So let's do this very quickly. So this is going to be for the reaction equals, it's hard to do anything quickly with this little like marker, but delta H of reaction equals, it's very difficult to draw straight lines, question mark. Okay, so it's going to be products minus reactants. And anything that has a coefficient in front of it, you have to multiply by that coefficient. So products is going to be this part over here, but the H2 is in the form it would exist in already as a pure element, so it's going to be 0, and we can see that also listed down here as 0. So just forget the H2. And also at room temperature, sodium is a solid, as we already know. We've already mentioned before, it looks like a loaf of bread. It's a pure element, so it is also going to be 0, as we see here. So all we're left with is the NaOH over on this side and the H2O on the left. The H2O is a liquid. And again, notice here, this degree sign means what? So I'll let you think about that. So we multiplied 2 times minus 470 here, and then that's going to be, so let's just very quickly write this out. So 2 times this minus the reactant. So the minus, and the only reactant we have left is the H2O, and there are 2 of those. So minus 2 times whatever H2O is, which turns out to be minus 470. So we're going to wind up with, let me try to finish writing this. Yeah, that's right. That's not right. So it should be minus 2 times H2O, which is 286, which is minus 286. I've already got the minus sign in there. So 2 times, let's just round these off. Okay, so round off this one to 300, or minus 300. So minus times minus is plus, so that's going to be plus 600. And then over here we have, let's round this off to 500. We've got minus 1,000. So we've got minus 1,000, and then we've got plus 600. So it should be about minus 400. Let's see if we're right. Next slide. And yeah, it's about that. So we were just trying to get a ballpark answer. So it's actually minus 368. So again, we're out of time. We're 5 minutes over actually. So we're going to move on now and do the word problems. So you might want to pause this video for just a few moments and look at this problem and make sure you understand. So in order to get what the delta H of this reaction would be, we just have to take the delta H of formation of the products minus the reactants. So let's stop here and I'll see you in the word problems.